All right, well, this is take 2 for today. I willingly admit to you that this section, 7.7, is such an easy section that I looked it over very quickly, a couple of different times, and selected the examples that we needed to work. But I guess I only about half read the examples and realized that they, the authors of the book, in their cleverness, actually pulled a sneaky little trick on me that I didn't catch until I was in the middle of recording. And then there were home distractions and things. And I basically just stopped the recording and started over because I was getting confusing to you guys. Now, so variation, what I had intended to do was just variation and no problem solving, meaning no word problems. Because I thought, didn't we have enough of that in 6.6? Well, the way they have cleverly designed this section, you can't really practice the material without using word problems. The plain Jane ordinary problems they give you are just for setup purposes. And then when it's time to practice, the only ones you can legitimately practice the math on are word problems. So they forced my hand. So I went back and erased some stuff. And then I also erased the problem that I was completely messing up myself. It was a beautiful moment. I was getting a gigantic number, and yeah. So let's start over. We're going to be talking about variation, and variation, there are about 3 different types of variation. The first and the simplest is called direct variation. The book gives an example of that from the world of geometry, which hopefully you're familiar with this formula. If not, it's not a complicated formula, and you don't really need to have used it or understand it deeply to grasp what they're talking about. So the formula for the circumference of a circle relative to its radius. So the circumference is the distance around the circle, like that. And then the radius of a circle is the distance from the very middle straight out to the edge. So circumference and radius. So the formula for the circumference of a circle is C equals 2 pi r. And I'm writing it again because I kind of drew over it in my first recording. Okay, so pi, we haven't used pi too much, if at all, in this Algebra 2, but pi is a constant quantity. It's a number. It's approximately 3.14. In reality, pi goes on forever. It's 3.14, I think 159, and numbers go on forever. Occasionally you'll hear about some genius who has memorized pi out to like thousands of digits. I think the supercomputers of the world can take it out to maybe billions of digits, but there's no end to pi. Okay, in Algebra 2, or maybe I think it was Algebra 1 for me, Algebra 1 or pre-algebra, I was allowed to just plug in 3.14 anytime I saw pi. And I'm going to do this here just to illustrate that it really is a number. So if pi is about 3.14, then 2 times pi is about 6.28. So what 2 pi or 6.28 is, it's just a number, it's a constant. And because we're doing variation problems, we're going to call it the constant of variation. And what that means is for any value of r that we plug in, the value of c is going to be about 6.28 times as large as the value of r. So if r goes up, c will go up by 6.28 times that. If r goes down, c will go down. But the up-down relationship is the important thing. R goes up and it forces C to go up. R goes down, forces C to go down. We say that C varies directly with R. And as I was mentioning, that just means if R gets bigger, so does C. I think it is, Matthew. Okay, another example that I threw in here while we're talking circles. The area of a circle equals pi times the radius squared. And I got overzealous with my circling there. there's the equation untampered with. Pi, or 3.14-ish, once again, the constant of variation. Here we're saying that a varies directly with r squared. So if r squared goes up, so does a, vice versa. Okay, so direct variation always means that one variable is a constant multiple of another variable or expression in terms of the variable, like r squared here. But one letter gets bigger, the other letter gets bigger. Constant multiples. So this practice problem, suppose that y varies directly as x, and then they give us a value for y, value for x, ask us to find the constant of variation and the direct variation equation. Okay, so here, the practice problems are just basically asking us to set something up. They're not actually giving us a problem to solve out completely, unfortunately. Now, you can see I underlined in orange there. Y varies directly with x, or as x. Here's what we do with that. That means to us that y is a constant multiple of x. So y equals some constant times x, and the letter that algebra or someone along the way has selected to represent the constant of variation is the letter k for some reason. I'm not sure why. I was in the earlier recording, I was guessing it's because using C for constant, maybe C having other meanings, I don't know. In higher order math, C is allowed to be the constant, so I'm not sure why it's not allowed to be the constant here, but who knows. So we've got y equals kx, and I was showing you that in the case of the circumference or the area of a circle, k was either 2 pi or pi, and then you had other variables playing the roles of y and x. All right, so they tell us that y is 20, while x is 15, and that enables us to divide out the 15 and get that k is 4/3. And notice here I went from 20/15 equal to k equal to 20/15. I prefer to see k on the left, and if it's just a simple equation, number equals letter, you can rewrite that as letter equals number. It means the same thing. Okay, so plugging that into our variation equation, y equals kx, that's all we can do. Ordinarily, in a true problem, we would be given another value of either x or y and asked to plug it in, but we're not. We have to save that for a practice problem. Now, I was not enamored with where they went in practice problem 2. So I dove back into the homework section to find something that I thought was a little bit more straightforward. So we've got this ton of words, but not really a ton of hardcore word problem type of stuff. The amount of pollution varies directly with the population. So P is pollution, N is population. This is, I think, what threw me off. I wanted P to be population. Kansas City has a certain population, and there's the tons of pollution that it produces. So find how many tons of pollution we should expect St. Louis to produce if its population is 348,000, then round to the nearest whole ton. Okay, so Kansas City has this population and this amount of pollution. Let's come down a little bit farther, and I erased my tracks so we can start fresh. So the equation, pollution varies directly with the population. That means pollution is a constant multiple of the population, and a constant multiple is always represented in this section with the letter K. All right, so Kansas City, and I'm going to write for my own benefit as I start scrolling down, people, pollution. So Kansas City has a certain population and a certain amount of pollution. Let's plug that in. So pollution goes over here, and population, people, is over here. And this will enable us to find what K is. I can already tell this is going to work out better. Now, the fact that they're asking us to round is interesting to me, something to keep in mind here. I got K down to, well, about this stage, even though I had the wrong number when I worked the problem earlier. And I'm going to grab the calculator and turn this into a decimal, because seeing that we're going to have to round this thing, yeah. Yeah, K is approximately equal to 0.588 or so. But we don't want to round at this stage in the problem. Now, when I grabbed the calculator the first time I worked this problem, I got 1.7. It was great, no rounding needed. Got to the end of the problem, got a whole number, no rounding needed. This problem is going to force us, this is a little more realistic. So I want to put in the notes, we don't, as a rule, round to the end, round till the end, because if we round K, we're going to introduce a little bit of error into our problem. We won't be working with the exact value, we'll be working with a rounded value. Now, what we can do, and this is what I missed earlier, we can, 13 apparently goes into both of those. Yeah, you can. I'll put it right back on the table, okay? So K is 10 over 17. This is the version of K that I would use. Let's see, P equals Kn. So P equals K N. That's our equation. That's where we were allowed to stop in our practice problem. Now here, St. Louis, how many tons of pollution? So what P should we expect for St. Louis if its N is 348,000? So P equals 348,000. And this is the point where you're probably going to end up rounding. Again, a realistic thing. These are real numbers. There's a source quoted down the World Almanac here. So real amount of pollution, real amount of people. So numbers are not going to come out pretty. So P is 204,705.8824. That's the number it comes out to be. But rounded, they wanted us to round, thank you, Matthew, rounded to the nearest whole ton. This 8 here is going to round that 5 to a 6. So 204,706 people. That is our, that's our population. Okay. Now, that was direct variation. That's the first and most basic type. The second type of variation that we're going to concern ourselves with is called inverse variation. And I'll just go ahead and put this formula up here. It's still y, k, and x, but this time instead of y equals k times x, it's going to be y equals k divided by x. And that's because inverse means there's an inverse, a reciprocal type of relationship between y and x. If x grows, meaning the denominator of your fraction grows, y is going to shrink. If y, or if x shrinks, y is going to grow. So that inverse relationship. Yeah. Yeah, I'll put it here on the edge of the table. Thanks for saying this. I'll put your water there where you can reach it, okay? Let me get the remote back over here. He likes to, we use Pandora, the music app, a lot around here, as I've probably mentioned, but for some reason, That drives us both crazy. Every so many songs, the picture blows up on the screen and it drives us crazy. No, I'll tell you later, babe. I've got about 15 more minutes, okay? Now, let's look at their cute little setup example here. And then I'll have to dive back, grab a word problem off the top of my head. Once again, my efforts to prep for this section were not thorough enough. Okay, suppose that B, the letter B, varies inversely as A. If B is 5, when A is 9, we want to find that constant. And we want to find the equation. And that's all we want to find. We're not going to be given enough information to work a complete problem here. So suppose B varies inversely as A. So that's where our problems always begin, with some kind of setup. B equals K, that's always going to be true. It's just a matter of where does A go? If the word inversely were swapped out for the word directly, A would go right next to K like we're used to. But now, with inversely, that forces A into the denominator. Okay, so B is 5 when A is 9. So we're going to find the constant of variation by very simply multiplying both sides by 9. So K will equal 9 times 5, which is 45, which means that the equation that we're asked to write down is just B equals 45 over A. There we go. That's it. Simple, right? No, I told you about 15 more minutes and you need to find your clothes so we can go outside. Okay, so let me come down here. Yeah, I'm going to just jump onto this problem. 32, okay. Yeah. So we've got the weight of an object that's on or above Earth's surface. And the weight of that object is going to vary inversely as the square. This is where it gets interesting. Of the distance this is a very wordy problem. The distance between the object and Earth's center. Okay, so if we've got a person and they weigh 160 pounds on Earth, we want to find the weight of that person and I'm just going to recopy the weight of the person 200 miles above Earth. All right, so rounding, we've got to do some rounding. This time we're rounding to the nearest pound. And then assume that Earth's radius, the distance from the center of the Earth out, is about 4,000 miles. So this problem, a little more complicated, but we'll take it very slowly. And that's for my sake as much as for yours. Now, there is a drawing in the book if you feel like you need that. I'll probably do my own drawing here. But if you feel like you need to see the way they drew it, flip back in there and check it out. So the weight of an object on or above Earth's surface varies inversely as the square of the distance between the object and Earth's center. That's a lot of words. That's a lot more words than we're used to when we're setting up in a variation equation. So I'm going to focus on like the weight of an object. So that'll be W. Weight of an object on or above Earth's surface varies inversely as the square of the distance. Okay, so the square of the distance. Notice it's not just varying inversely as the distance, it's varying inversely as the square of the distance. I'm going to let distance be d, and the square of the distance is d squared. That's my basic setup, and really in a way, things look a whole lot less weird once you've gotten that down on paper. Particularly in this problem where we had to just shove a bunch of words to the side and pull out the essence. Weight equals k over d squared. Now we will have to remember the distance is between the object and the Earth's center. So that's where the radius of the Earth comes in. So we're going to have a radius of 4,000 miles. That's going to look like this. And at the beginning of the second part of the problem, it says a person weighs 160 pounds on Earth. So he's on Earth's surface at the beginning of the problem. So his weight, the weight of the person on or above the Earth's surface equals k over, and then d squared, the distance between that person who is our object and the center of the Earth, that's just the Earth's radius. Okay, so kind of an interesting setup here. Now, k, you can tell, k is going to become gigantic here in a minute. It's going to be a whole number, but it's going to be a gigantic whole number. Again, starting to play with these real numbers. All right, check out what k is. And let me see, that is 1, 2, 3, 4, 5, 6, 7. Count my zeros. Yeah, so if I square that, that makes 6 zeros and then 1 extra. So there's k, beautiful thing that it is. So our formula, and the minute you have k, put it into that formula no matter how ugly it is. That's what we're dealing with, okay? Now, the rest of the problem tells us we want to find the weight of the person, so we're going to be looking for W, but now that person has moved 200 miles above Earth. So we've got the 4,000 plus the 200. Now the person is like right out here, okay? So 4,200 is the distance, that D, between the person and the Earth's center, because the distance is always measured relative to the center of the Earth. Okay, so we want W equals K. I'm so sorry that we have to write this number so many times. 4,200 squared. Not yet, about 10 more minutes now, okay? No, let's see. The big hand will go on the 2. Okay. I'm going to teach 2 different things. Just watch the big hand, okay? So W is about 145.1247166, at least according to my calculator. They want it to what? The nearest pound. Okay, so this 1 is not going to turn that 5 into a 6. So the weight is still going to be 145 pounds. And just as a verification from my very limited understanding of science, the farther you get away from the Earth, the less you weigh. So yeah, if you started out at 160 pounds on the surface of the Earth, and then you get on a rocket, your weight drops as you get farther from the pull of the Earth's gravity. Okay, so that was a fun and exciting problem. Again, thank you so much, textbook, for foiling my plans of having a very simple problem here. Okay, now.
Are you finished, Mama?
Okay, now. What am I looking for? Joint variation. This is our 3rd type.
I'll
I'll tell you later, okay?
the iPhone.
Joint variation is instead of where you have y equals kx. Okay, Matthew, you need to go play again. Okay, 10 more minutes. Okay, sorry about that. Joint variation. This is our 3rd type. Joint variation is like direct variation, but with more variables. You can see here that y is varying jointly with x and z. It's like it varies directly with 2 things. And pardon me for a second while I find a suitable problem. Page 433. Okay, the number of cars that are manufactured, and they say manufactured on an assembly line at a General Motors plant. I'm just going to say number of cars made at this plant varies jointly. So let's just get to the good stuff. As 2 things. The number of workers and the time they work. So there's our X and our Z. Number of workers and the time they work. All right, so now we get down to the numbers. If 200 workers can produce, they say, I'm going to say make 60 cars in 2 hours, find how many cars they can make in 3 hours. Okay, so the number of cars made at a plant varies jointly as the number of workers and the time they work. So number of cars varies jointly as number of workers and the time they work. You can see me circling the letters that I'm going to end up using there. So number of cars. Honestly, let's see, I might rethink this. Maybe it would be more descriptive to actually circle the C here. So the number of cars varies jointly as the number of workers and the time they work. That's the way my brain works. If a different letter or letters jumps out at you, feel free to use those. So if 200 workers can make 60 cars in 2 hours, notice how they kind of scramble the order of what they give us. Find how many cars they can make in 3 hours. So the C will be our unknown in the next part of the problem. So right now I've got 60 equals K times 400, which K equals 60 over 400, or 6/40ths or 3/20ths, and I probably would leave that as 3/20ths. They didn't say anything about rounding. I know 3/20ths would come out to be this nasty decimal thing in the calculator. So my formula right now, C equals K times W times T. And then they tell us, find how many cars they can make in 3 hours. Now the number of workers hasn't changed. It's still 200 workers. So the only thing that's changed is now the 3 hours is my time. So let me say C equals 3/20th. I've got 200 workers and now I've got 3 hours. Okay, and you can grab your calculator at this point. A lot of times I like to clean things up. So 20 into 200 is 10. 3 times 10 is 30. 30 times 3 is 90. So 90 cars should be what I come up with as an answer. Yeah, and it is bigger because the time was longer. Give them an extra hour, and they were able to produce more cars. Okay, now I had told you, I think off the top of my head, that there were 3 types of variation. I think I was combining something that the book splits apart. They talk about joint variation and, what do they call it? Combined variation separately. I think I was kind of lumping those together in my mind. But it's good to break them apart when you're just learning this, even though maybe it makes it feel like you have to learn more. This is when, and there's not an equation for this, because this is when there's going to be some combination, and that could change problem to problem. Of direct, inverse, and joint variation in the same problem. But what that combination is not something we can nail down. So, and believe it or not, we can actually end on a practice problem here. All right, so suppose that y varies directly as z and inversely as the cube of x. So there's our combination. They have combined direct variation and inverse variation. just, I don't know where my reading ability is. Oh well, extra problem, extra bonus. If y is 15, this is still the setup. I don't know where I was reading or thinking I was reading a complete problem. Y is 15 when z is 5 and x 3. Find the constant and the equation. So I'm going to have to dig for another problem. I was probably reading the example right above it, and yeah, this gets really weird. The way the examples and the practice problems correlate to each other in this section is not the way they usually do. All right, just keeps it interesting for all of us, I suppose, particularly for you guys trying to follow along with this. Well, not quite. Y varies directly as z. So this is the way, the very first part of this is the way that we would have ended our setup initially with the direct variation, but inversely as the cube of x. Directly as z and inversely as the cube of x, yeah. Just like with the joint variation, you only ever need 1k per problem. So if there's a piece of good news, it's that. So if y is 15, when z is 5 and x is 3, not forgetting to cube that x, find the constant and the equation. And then, so k times 5, 3 times 3 is 9 times 3 is 27. So what I can do, 5/27 is the fraction sitting there with the k. Let me flip it to 27/5, multiply both sides by 27/5. The 15 and the 5 reduce. I think that is 81. K is 81. So the formula y equals 81 z over x cubed. Now, am I going to get lucky and find a lovely little problem? Almost. Matthew, thank you for your patience. Thank everybody for their patience. Varies jointly. Okay. Yeah, struggling here to find as many problems as I need. Okay. Final problem. The maximum weight that a rectangular beam can support varies jointly, et cetera, et cetera. I'm going to say the max weight that a beam, who cares if it's rectangular, and this one gets interesting because it's got joint variation in there, jointly as its width. So remember, when you see the word jointly, two things are going to come in a row after it. So as its width and the square of its height. But wait, there's more. It varies jointly as those two things and inversely as this thing. And I'm just not loving the grammar in this sentence. I don't know of a better way they could have said it, but it feels a little bit like a run-on when I'm writing it out. Okay, so we've got the beam here. So if a beam that is half a foot wide, interesting that they're choosing feet here and not inches, 1/3 of a foot high. They must want us to use fractions. And 10 feet long. Can support 12 tons. I'm putting a comma in there. Again, the grammar is starting to irk me. Find how much a similar beam can support if this similar beam has the following dimensions. 2/3 of a foot wide, 1/2 a foot high, and 16 feet long. Oh, I'll let this in. That's a lot of writing, even with me taking out words. Okay, so fittingly enough, we're going to end on the hardest problem we have yet seen. This is my last problem, Matthew. Did you find your clothes? Okay, so the weight that a beam can support varies jointly as its width and the square of its height. This is interesting. So I've got weight and I've got width. So I need to think very carefully about the letters that I use. Okay. You can use, if you are brave, you can use big W and little w, or you can choose a completely different letter, and it's kind of up to you. I am going to, no, I'm on my last problem. Okay, give me a few more minutes. I am going to just select D here. So the max weight that a beam can support varies jointly as its width and the square of its height. So joint variation is like direct variation all on a line, as its width and the square of its height, width and the square of its height, height squared, and inversely as its length. So that just means length is going to go down under there. And I'm writing a cursive L because I don't want to write a regular L and have it look like a 1. So all kinds of pitfalls in this problem. This is just lovely. So if a beam, a 1/2 foot wide, max weight a beam can support. So there I was already messing up what the W was. Okay, so it can support 12 tons. So wide, width, that was my D. So a 1/2 foot wide. And then I'm going to have something squared. Okay, so 1/3 foot high and 10 foot long. So out of all that, let's find our K. Very carefully. So K is next to a 1/2. If I square the 1/3, I get a 1/9. And I've got this 10 here, and I'll just go ahead and tell you guys what I'm going to do with the 10. I'm going to multiply it to both sides right off the bat. 120 equals K times a 1/2 times a 9. Okay. So that's 120 equals K times 1/18. Last thing I need to do, multiply both sides by 18 and I'll have K. No, not yet. Bring me the clothes that you picked out and let me look at them. Okay, Matthew? So 2160, there's my K that I'm going to use. So this lovely equation that I'm so fond of, W, the weight, equals 2160 times the D times the H squared over the L And I did that from memory, so let me make sure. Yeah. Okay. Very nice.
So I'm gonna push it.
Well, not yet. I'm not done yet. Do you need what? Do you need clean socks? All right. So now, find how much a similar beam can support. Yeah, sit here since I'm almost done. 2160. If that beam is 2/3 foot wide, 1/2 foot high, and 16 feet long. Okay, let's see here. 2160 times 2/3 times 1/4 over 16. Let me borrow this real quick, Matthew, so I can find out what this number is.
Why? What am I borrowing?
Oh, nice. Okay, so this will reduce with the 2160.
Down.
Okay, gotta be patient for a
That
couple more
down.
minutes.
Put it right there.
35 times 2/3
That thing.
times
Here,
1/4.
Mama.
No, I'm not gonna put it there. All right, now this is 135 times 2
I'm trying to get it off.
12ths. And this is 135 times 1/6. All right, so the weight there is going to be 22.5. They don't tell me to round it. Tons. And that is it. Okay, so thank you for bearing with me there.
Can I push a button?
With this craziness and with this section being more confusing and set up way differently than I thought it was. The good
Can
news
you push a
is that
button?
we are done with chapter 7, and that's got to be a good thing. That's got to feel good. So I am going to, let me make sure I end this recording, because goodness knows I don't want to have to do that for a third time. Okay, so